Okay, so good morning, everyone. So my name is Juan Sierra. I am a senior researcher here at ICN2, working in the physics and engineering of nano devices group. I will be chairing this very first session of the morning that is focused on spintronics. So we have two speakers. So I will introduce later. So let me just to organize this a bit about the questions. So we will have questions after the talks. So for those that are here, you can directly ask the questions. And for those that are from home and connected via Zoom, it's better if they can just pose a question on the chat, and then the chair will read the question. So with this, let me start by introducing our first speaker, which is Onur Avci. So he's very well known here in ICN2. So Chan is a principal investigator in the Institute of Material Science here in Barcelona at ICMAB. He received the PhD degree in Zurich, ETH Zurich in 2015. Indeed, he started the PhD here at ICN2. And then he worked after the PhD at MIT from 2016 to 2018. Then he moved back to Zurich, and he was working there from 2018 to 2021. And then after that, he joined ICMAB. He's recipient of multiple prizes. Just to give you some of them, he's a recipient of an ERC starting grant, of the 2021 UPAP Young Scientist Prize in the field of magnetisms. That this is a very renowned prize on the spintronics and magnetic community. And he also received the ATH medal for outstanding doctoral thesis. So of course, I mean, it's very well known on the spintronic community, and he just is focused on in a broad subjects in spintronics and magnetism, especially on electrical control of magnetization. He's an expert. I will not say that this is an emergent, but is already a very well-established researcher on spin-orbit Torque phenomena in magnetic multilayers, spin currents, and magnetic and memory logic devices. So with this, Chan, the floor is yours.
Okay, thank you very much, Juan, for the very nice introduction. And yeah, it's a pleasure to be here at ICN2. Do we have a laser pointer? It's a great pleasure for me to be here, where my scientific research journey has started in 2011. I was a PhD student back then, so I basically did half of my PhD here at ICN2, and then I moved to Zurich. And finally, most of the things that I will be explaining here, actually, they have initiated at ICN2 about 10 years ago. So today, my talk will be about trends and opportunities in metallic and insulating spintronics. So when I was writing the abstract, I think I was quite daring. So I don't think I can give you like a full insight onto the topic, but I can only tell you maybe the tip of the iceberg, because it's a very broad topic, metallic spintronics and insulating spintronics. But I will just try to give my perspective and some highlights from my research background. All right, so magnetic materials, actually, they play the vital role in developing densely packed, high areal density storage devices. So that, as you can see here in this example, that in magnetic hard disk drive, actually, it can store like gigabytes of information, and in engineered ultra-thin films, and it's purely based in a non-volatile magnetic phenomenon. So it's it's basically the beginning of the computer era. So how they have boosted the storage density and also computational power of the modern computers. So hard disk drives, it is actually consists of several elements. You see here you have a recording medium here, which basically stores the magnetic information in magnetic domains. And you have a inductive write head, which writes the magnetic, well, which changes the magnetic polarization by applying a small field here. And you have the GMR read head, which can read the magnetic information here. So this actually, the miniaturization of such scheme was enabled by the invent of the giant magnetoresistance. The giant magnetoresistance is a magnetoresistive phenomenon occurring in magnetic multilayers due to the spin-dependent scattering of charge carriers of the electrons in this specific case at the interface and bulk of the ferromagnets. So here you can make a few nanometer films that is consisting of two ferromagnets separated by a non-magnetic material. And depending on the relative orientation of this ferromagnetic materials magnetization, you can have either a low resistance state or a high resistance state. So the change in the resistance between these two states is actually giant. So it's about 100%. So this allows detecting a tiny magnetic fields, which allowed basically building these tiny read heads, GMR read heads, to read the magnetic data in these hard disk drives. And this is considered to be, well, this discovery happened in the late 80s, and it is considered to be the beginning of spintronics. So this magnetoresistive reading was so efficient that it has boosted the areal density of storage from tens of megabits to tens of gigabit per inch square. And this tremendous increase actually started this computing revolution in the 80s and 90s. And this was recognized by the Nobel Prize Committee. And these two men, Albert Fert and Peter Grünberg, thanks to their discovery of the GMR effect, they were awarded the Nobel Prize in Physics in 2007, which is 20 years after they have actually discovered the phenomenon. So it was acknowledged much later due to this contribution to the computer technologies. So in the conventional way of hard disk drives, like writing and reading magnetic memory, magnetic data, you need three different elements. You need a magnetic medium, which where you store the information, but you need also an external like magnetic field, and you need a magnetic field sensor, which is the GMR sensor. But these are all separate units that are basically brought together in a proximity, but they are not in contact. So therefore, the final device, final application, it will be ultimately limited by the dimension of these elements, the speed of these elements, and the power efficiency of these elements. So there's a need for merging these three different elements into a single device, which would be basically like a solid state data storage, where you can electrically write and read the information locally on a single device level without needing all these extra elements. Therefore, going from mechanically moving magnetic disk into a solid state magnetic memory. So this brings me to the outline of my talk. So basically, this is like the quest of solid state memory. It has boosted like the spintronic research in the past 20 years or so. And in the first part of my talk, I'm going to talk about some early concepts of spin currents, because this is vital for making high efficiency data manipulation. And then in the second part of my talk, I will talk about SpinOrbit Torques, as also briefly mentioned by Juan. And then I will transition from conducting spintronics to insulating spintronics, where we see some opportunities that is not available in the conducting ferromagnetic counterparts. And then I will finish my talk by some conclusions and prospects. So the first part, okay, just to briefly explain spin currents. So spin currents, basically, you have, I have to first introduce the charge current. So when you apply an electric field into a non-magnetic conductor, so you will have the charges moving across this along this electric field, and the spin. So since there's no there's no mechanism to polarize the spin of these charge carriers, the charge flow will be basically like will have a spin, like zero spin polarization. However, if you do the same experiment in a magnetic conductor, due to the imbalance between the minority and majority states of the bands, you will have a net spin current that accompanies the charge current. So this is an one easy way to generate a spin polarized charge current, or let's say a spin current, but that always comes with a charge current. But the ultimate goal here is to be able to find mechanisms that could lead to a pure spin current without moving charges, which will mean that you need to be able to move these charges with oppositely polarized spin in different directions, so that you have a net spin current but no net charge current occurring. So this is basically lies at the heart of spintronic memory devices that I'm going to explain later on. So let's talk about the earlier concept. So the spin current was initially obtained by passing a charge current through a ferromagnetic layer. And if you make a device like this, where you have one ferromagnet that basically acts like a spin source, and you put a spacer in between this with a second ferromagnet, then you can, the spin polarization of the conduction electrons going through this first ferromagnet can act as a torque on the second ferromagnet. Therefore, you can control the magnetization state of the second layer, which I'm going to call it free layer, because that's what the one that you want to switch or you want to manipulate, and this will be your fixed layer. So you can engineer this kind of materials to act to bring some spin angular momentum from the first layer to the second layer and switch it. And these other ways of using the spin polarized current is in a single ferromagnetic layer if you have a domain wall. So if you have a domain wall, then the conduction electron that will conform the local magnetic moments and in the material, therefore, when it passes through this domain wall, it will also exert the torque on the spin of the domain wall, and it will move it eventually after a certain threshold current. So these two are basically the first prediction and observation of spin torque phenomenon, which which is basically the simplest way of generating a spin current in a material and also manipulate the magnetization. But that is always accompanied with a charge, and that's only limited to conducting materials. So this kind of this way of generating or manipulating magnetization has inspired some scientists to build a memory device called a magnetic random access memory. A magnetic random access memory, basically, it's an array of these tiny magnetic tunnel junctions where this magnetization, well, the information is stored in this magnetic orientation, and you can basically, by adjusting the current passing through each of these layers, you can switch the magnetization, and also you can use a lower amount of current to read the magnetic data by using the effect of tunnel magnetoresistance. This is basically the tunnel counterpart of the GMR. You can also use a alternative geometry to use a domain wall motion. So basically, you are still talking about the same kind of MRAM, like a spin MRAM architecture, but this time you have okay, this stopped working, unfortunately. So this time you can move the domain wall underneath that tunnel barrier and change the relative orientation of the magnetization between these two magnetic layers. And this can also be another way to basically control this spin torque MRAM devices. Okay, so the another way of using this current induced domain wall motion is to build a so-called racetrack memory, where you can basically, in this kind of devices, you can inject some current and move collectively all the domains in the material, such that you can store multiple bits of information in a single wire, and you can just put like a read head in the proximity and read the domain information at that specific location, just right at the bottom over there. So these are the early concepts of using current-induced spin torque phenomenon. Can you? Okay, so this brings me to the SpinOrbit torques, which is basically a more like a newer way of generating spin torques on magnetization. And also it's currently the state of the art of magnetic manipulation methods. So pure spin currents can actually be obtained by various physical phenomena. One of them is what's called spin Hall effect. Spin Hall effect is an effect that is generated by spin orbit coupling in materials with large spin, materials with large spin orbit coupling. And it turns out that when you inject a charge current into the materials, this charge current will undergo spin-dependent scattering, and then spins with opposite polarity will accumulate at the opposite interfaces of the material. And this is a way to generate a spin current that travels orthogonal to the charge current. So the charge current goes in plane and the spin current will go out of plane. So this is, as I explained earlier, this is basically a perfect scenario to generate a pure spin current in a material that is more flexible than like the spin polarized current I explained earlier. So, but spin Hall effect is not the only effect. So there are other alternatives. For instance, Rajba-Edelstein effect, which is using the broken inversion symmetry at the interface that basically polarizes the charge current going through. And this occurs at metal-metal interfaces or metal-oxide interfaces or even oxide-oxide interfaces. So there is you have a net, due to the symmetry breaking, you have a built-in electric field. And due to the relativistic effect, a charge current going through the electric field feels a magnetic field and it tries to align to it. So you can also harness this kind of spin accumulation in devices. And finally, I would like to mention about the topological surface states in topological insulators. So because of the special band structure of topological insulators, you have no charge current going through the bulk of the material, but only surface is conducting. But it's not only conducting, but it's also spin polarized. So it's purely spin polarized, and it's extremely robust, topologically protected spin current generation in materials. And it has been also demonstrated that you can generate very large torques on the magnetization by using this mechanism. So all these effects and others as well that I wasn't, I did not mention are collectively called now spin orbit torques. And the spin orbit torques are basically gives rise to two types of torques on the magnetization when you inject. So it's the most like simplistic case. You have a non-magnetic ferromagnetic layer bilayer, and the passing charge current can apply large damping-like and field-like torques on the magnetization with the symmetry that show you here. And these torques are basically can be measured because they are also generating an effective field called like this BAD and BFL here. And the materials that we measure the figure of merits of different materials. That basically is how much spin current you can generate by from a unit charge current. So that is the basically the fraction of spin current to the charge current that you inject into the system, and that's called spin Hall angle if you consider just the spin Hall effect. And in the case platinum is about 10–20%, and in the case of tungsten you have about 25–40%. You have also large effects on tantalum, but somewhat lower effects if you go to materials with lower spin orbit coupling, such as palladium. Actually, this kind of magnetic manipulation by spin orbit torques have the first initial research was performed here at ICN2 in 2011 in this paper here. So you have my PhD supervisor back then with his colleagues, his teammates, was able to control the magnetization of a single ferromagnetic layer by simply applying an in-plane charge current in this material here, that is platinum, cobalt, aluminum oxide. And this has followed up with other materials such as tantalum, for instance, that they were able to not only switch the magnetization, but they could also build like a magnetic tunnel junction and read the magnetic state by using the tunnel magnetoresistance. Okay, so the early concepts of MRAM was based on spin transfer torque because of the large current that you need to send through the tunnel barrier. So these kind of devices had somewhat limited endurance because these tunnel barriers cannot be thicker than a few nanometers. And if you send a large amount of current And if you cycle the device over tens of times or millions of times, then you have a risk of breaking this tunnel barrier. However, SpinOrbit Torques now, it offers an alternative geometry where you can just inject an in-plane current. There is therefore relieving the stress on the tunnel barrier, and you can also make it with a perpendicularly magnetized layers, and well, which is also convenient for scalability. We indeed later on demonstrated that this kind of SpinOrbit Torque based tunnel junction can work with materials such as CMOS compatible materials such as tantalum, cobalt iron boron, and MgO. And we have demonstrated here that it's a perfect reproducibility of the switching, and with the TMR, well, the tunnel magnetoresistance ratio is just over 50%. We also investigated other directions, such as how fast we can switch the magnetization. So we were able to go down to 180 picosecond switching. So that's very fast in devices that is only a few hundred nanometer in diameter, in lateral size. And but the state of the art actually of the SpinOrbit Torque switching is not this, it's even further. That is basically just 6 picosecond. Can you please? That was obtained basically this kind of little bit more sophisticated devices where they used like an Austin switch to trigger a very, very short pulse, and they were able to switch the magnetization of a magnetic element by like right under 10 picosecond. And if you want to have more about an update about this, what's the status of the SpinOrbit Torque MRAM, you can also check these 2 papers here. Okay, SpinOrbit Torques can actually do more than just switching the magnetization. You can move domain walls fast and efficiently. You can also, can you please, you can also generate skyrmions. So skyrmions are basically topologically protected spin textures that are in nanometer size, and you can generate skyrmions and move skyrmions in suitable engineered materials by just using SpinOrbit Torques. You can also, by combining domain wall motion and SpinOrbit Torques, you can also build some nanomagnetic logic circuits that have been just recently demonstrated in this paper in Nature. That's also a nice way of doing non-volatile logic, non-volatile logic element. You can also excite and amplify spin waves in this spin wave waveguides. That is also very good for magnetic applications, because magnetics has emerged basically as a beyond CMOS computing platform where you use spin waves as carriers of information, and you can use both this amplitude and phase information by basically building both memory and logic type of functionality. And ultimately, this spin Hall effect has been also used in nano oscillators. So you can also basically just using a DC current, you can excite some some high frequency oscillations in this nanometer scale nano oscillator, which is also very useful for applications. So all these advances in the past decade has enabled by SpinOrbit Torques, could lead to solid state racetrack memories, not only on domain walls, but also on skyrmions, non-volatile logic elements, but also skyrmion-based neuromorphic computing, beyond CMOS magnetic applications, reservoir computing, and terahertz antennas, and many more. So these are all enabled by using basically this current in the SpinOrbit Torques. So that brings me to the to this third part of my talk, so which basically involves more research updates from my recent past. So as you can appreciate that most of the experiments that I have shown you, most of the examples, they relied on conducting ferromagnetic materials. But do we actually need conducting ferromagnetic materials? And the answer is no. So there is actually some transition, or let's say branching, towards more insulating spintronics. I mean, this is important because insulating materials offers much more flexibility in terms of most of the material properties and engineering. discovered some 60 years ago. So I would like to focus on magnetic garnets, which is basically mostly like my research is focused on magnetic garnets, which is just one family of magnetic insulators, but it's a very useful family of magnetic insulators. So magnetic garnets are this kind of, well, have been discovered in the late 50s and studied like extensively in the 70s and 80s, and now we understand very well their properties. So just briefly to give you an idea, like the unit cell is actually a complicated one with 160 ions, but in a simplistic way, it consists of this tetrahedral and octahedral sites and dodecahedral site, and the spins are coupled in the way that I show you here. So you have here and here you have the iron that are coupled anti-parallel due to the super exchange interaction, and you have the third element here, which could be a magnetic rare earth element that couples anti-parallel to that tetrahedral site up there. So because of the flexibility of choosing this dodecahedral site element, we could choose it from a magnetic material or non-magnetic rare earth material. Then we have an well, large spectrum of materials that could be used to tune the magnetic properties of these materials. Such as you can see here, for example, that the saturation magnetization, it varies tremendously, but also very controllably depending on which material is incorporated into this unit cell. In terms of magnetic properties, garnets actually they have the record low damping. So yttrium iron garnet is the lowest damping of magnetic materials that we know of so far, and also it's quite tunable. So you can also make it larger if you wish to, and that depends on the application that you are looking for. Then it also has tunable anisotropy. You can have them in plane anisotropy or out of plane anisotropy, and anisotropy also doesn't depend on the interfaces. Mostly in the case of conducting materials, it depends on the interfaces, but this is a bulk effect, so you can have it out of plane and have flexibility over the thickness of the material that you can grow. Then you have also tunable saturation magnetization, tunable magnetic compensation, tunable angular momentum compensation. That would be also useful for ultra-fast magnetization dynamics. On the structural side, you have very high crystallinity. You have single crystal epitaxial growth of, for example, in this case, thulium iron garnet on GGG on substrates. And because this is a natural oxide, and because you are using this as a first layer, so this could lead to some flexibility over device design that you want to make, because this doesn't get oxidized. This is basically, you are using this as a substrate, and you can build any different kinds of device geometries on top. Thank you. And then, of course, and here basically is everything I said before. So there's just a summary here that you have many different attributes on the well, different properties that is very useful for spintronic, but also beyond spintronic, that is related to, well, garnet structures. So my research is mainly focusing on the perpendicular magnetic anisotropy, and this is there's a very big progress in the last years, because perpendicular magnetic anisotropy, you need to engineer it. You need to have some lattice well, engineering of the materials. But starting from this 2016 paper, there is a big number of materials that you can grow sub 10 nanometers with perpendicular magnetic anisotropy, and that could be very useful for most of the spintronic phenomena that I explained you previously. So the but now you are wondering, okay, so if you are talking about insulators, so what's the mechanism to basically read the magnetization? So there is a nice effect called spin Hall magnetoresistance, which is basically when you put a material with large spin Hall effect, such as platinum, and send the current, although platinum is not magnetic, the spin current that is produced due to the spin Hall effect will feel the magnetization, and it will give rise to both a longitudinal magnetoresistance signal and also transverse Hall effect signal. And this Hall effect signal can be nicely measured in devices that looks like this. So you only have current going through platinum, but then you can nicely probe the outer plane. You know, you can nicely get the outer plane hysteresis by using an outer plane field sweep, or you can do an in-plane field sweep to get this coherent rotation of the magnetization. So in a local geometry, this is a very powerful technique to measure the magnetization. And now, okay, spin-orbit torques, basically, since the spin current from spin Hall effect, it travels in the orthogonal direction to the charge current, it can also penetrate into this magnetic material even though it's insulator, and it can lead to magnetization switching. So I will, here you can see that, for instance, in the presence of an in-plane field, which is required to break the rotational symmetry of the switching torque or the damping like torque, then you need a small bias field. And while using this bias field, you can switch the magnetization between up and down state in a reproducible way by just changing the current density that is going through the platinum. And you can, by making many of these measurements, you can also build this switching diagram. You can also do switching at the nanosecond scale, although the measurements are not as they are not looking as nice as they should be, but there's some signatures of very efficient switching also at nanoscale, and also efficient since the switching is mediated by nucleation and domain wall motion, that also has some signatures on fast domain wall motion. So these measurements, these early measurements that we have done, it shows very large spin-orbit torques can be induced on the magnetization in these insulators, and provide fast and efficient switching. And it has very low external field requirements. Actually here, that's down to 2 Ørsted, which is very, very small, and also some signature of fast domain wall motion. So because we saw some signatures on the switching measurements, we wanted to study the domain wall motion. So I'm going to give you a little bit more larger, how much time? 10. Okay. So I would like to give you some research highlights from the latest, in the past couple of years. So one thing that we did is to study the domain wall motion in this thulium iron garnet platinum bilayers. So here, okay, I'm gonna go a little bit fast because I have still many slides and I would like to show some interesting ones. So this experiment was basically to show you that once you have a magnet, this is the device we used, of course, and we use a laser spot to probe the magnetization at this point. And here we use a nucleation current to nucleate a domain wall here. So nucleate a domain and a domain wall here. And by running a charge current along this wire, we can move this domain wall. So this is the hypothesis. So we tested this hypothesis, and we indeed found the evidence that this current can have an influence on the magnetization, on the domain wall here. Is exemplified in this data. So, and the effect that the current creates on the domain wall, it actually scales linearly with current. That's further reinforces the hypothesis that we have some torques acting on the domain walls. This was a surprise for us because normally, typically in a magnetic material, if the domain magnetostatically, domain walls are of block, what's called block type, which means you have an up and down magnetization domain, and it's basically from going up and down, it will rotate like this. But due to the chiral Jeloshinsky-Moria interaction that we discovered at the interface of this, at the interfaces of this thulium iron garnet, it turns out that the domain walls are nail type, meaning that it just rotates like this. So this is the current line, and this is the rotation of the domain wall. And this is very important because otherwise you don't have any effect of the spin-orbit torques on the domain wall. So having a chiral interaction and having a DMI stabilized nail type domain walls is very important for domain wall motion applications. This also basically, I will maybe skip that because that's basically how we quantified how much effective DMI field was acting on the domain walls, and it turns out to be on the order of tens of Ørsted, which is not so much, but enough to make it fully nail type. But most importantly, we have measured the domain wall velocity. Well, we studied the domain wall velocity as a function of current, and we found out 2 very important things. Is that first, the critical current that starts the domain wall motion is extremely low, on the order of 10 to the 10 amps per meter square. That's typically 1 order of magnitude lower than in the conducting ferromagnets. And the velocities can go up to 1 kilometer per second, which is also kind of one of the highest at the time that we published this paper. So, and this is enabled by the ferrimagnetic nature of the materials, because you have these two lattices that couples anti-parallel to each other. So now I'm just considering the iron lattices that are anti-parallel. So you have these two magnetic lattices. Because of the well, the damping like torque tries to tilt these two magnetic lattices towards this torque direction. However, the exchange interaction is so strong that it restores this damping like torque effect. Therefore, the domain wall doesn't, change its orientation, so it just remains as a nail type domain wall, even though you inject a very high current density. And due to that, we do not observe a saturation of the domain wall velocity, because in this physics, if you had only one sublattice, just one magnetization direction, then it would quickly saturate, and then you will have no more further enhancement of the domain wall velocity. But because of this exchange coupling enabled by the ferrimagnetic character, then you also have like non-saturating, like extremely large velocity of domain walls in these materials. Okay, I think I will just skip this part of the talk, because that's going to take too long to explain. And let me briefly state my conclusions first. So I hope that I was convincing that we've had some tremendous progress in current-induced magnetic manipulation during the past decade, initiated by current-induced spin polarized currents, spin transfer torque, but also later on SpinOrbit torques. And this transition from spin transfer torque to SpinOrbit torques has created some highly fertile ground for novel concepts and technologies, especially for ICT applications, which why we are here today. And the material spectrum is not limited to metals, which is basically a handful of materials, but also to great flexibility is offered by magnetic insulators that I just gave you one example on the Garnets, but even Garnets has a very large family, and this could be extended to other insulators as well. So some prospects. So this is my view. So it's purely personal. So I think that we have to make progress in these 4 different categories. So one is the fundamental understanding of spin physics. So we need to understand better the charge spin relations in complex systems and try to increase the figure of merit and not only basically limit ourselves to high spin orbit coupling materials, but also some alloys or some other phenomena such as subtopological insulators or vial semi-metals or transition metal dichalcogenides, which all offer very promising results, or let's say we have seen some promising results from these. Spin transport through interfaces, as you have seen, that everything that is related to spin orbit torque, it is concerned interfaces. So you should be able to inject large spin currents through interfaces. So it's very important to engineer these interfaces. And we need to understand better the spatial and temporal limitation of spin orbit torque driven switching mechanisms, because I mean, for so far, we are only limited by instruments, but we don't know the fundamental limits, how fast we can do. Then we have to explore the dependence of spin transport on tunable properties of materials. We have to explore beyond spin currents, also orbital currents that can also act like a spin orbit torques on the materials. And also we have to be able to find means to engineer these chiral magnetic interactions, which ultimately leads to spin textures such as Néel domain walls and skirmels. On the material sides, we have topological insulators, semi-metals, 2D materials, very important, and alternative magnetic materials such as antiferromagnets, which would be also allows very ultra-fast operation, ferrimagnets and magnetic insulators. We need to combine the spin orbit torque physics with complementary approaches such as gating, for example, ionic gating to control magnetism by voltage. We should be able to harness multiferric degrees of freedom using piezoelectricity, for instance, to tune magnetic properties could be one way. Harnessing also thermally driven spin currents and not only charge driven spin currents, and use also flexible materials. On the devices and technological concepts, I think I've gone through all of this throughout my slides, so there's no need to restate those. But yeah, basically there's a lot of opportunities for us to enjoy spin-orbit torque physics and the materials surrounding it. And I would like, before finishing, I would like to thank my postdoc supervisor, Jeff Beach and his team, and our collaborator at MIT, Professor Caroline Ross and her team, and my PhD supervisor and postdoc advisor, Pietro Gambardella at ETH Zurich, which gives me continuous support on all stages of my career. And before finishing, I would like to mention that, yeah, I've recently, initiated this ERC project at ICMAB just over a year ago called Magnetic. So if you want to have updates or want to have more information, you can contact me or consult this website. And with this, thank you very much for your attention.
You presented early on some very impressive dynamic results with 6 picoseconds.
Yeah.
I'm wondering, where's the limit and how fast can it go? I mean, where are the elements that set the physical limit?
Okay, so the limits were actually magnetic damping is one of the limits, because that's what basically, so you need to be able to engineer a material with very high damping such that you don't initiate some precessional dynamics to the magnetization, which will take a long time to establish. So damping is one parameter, critical parameter. And in the case of platinum cobalt is a very high damping material. Therefore, it's suitable for this kind of switching. So that's one way. But it's also surprising for us to see that big jump from 180 picosecond, which we seem to understand why and how, so we can simulate, etc., to go to 6 picosecond. This is a big jump, and it's still new for us. I mean, that's. I mean, I was not involved in this project, obviously, but it was quite impressive.
Further questions? I don't know if we have. Okay, Aitor.
General one about the prospects. You mentioned the 2D materials as possible shot source. Do you think there is any room also for magnetic as magnetic components?
Magnetic 2D materials.
Yeah. Because you didn't mention them as possible
yeah,
magnetic
yes.
materials. Do you see them any possibility for that?
I mean, yeah, that's well, if I say something, it would be quite daring, because I'm not really, I'm not into the physics or fundamental understanding of 2D materials. But what I understand is that the main limitation of 2D magnetic materials is that they work at low temperature. So once you bring them to work at room temperature, I'm sure that because of the perfect interface, that this epitaxial perfect interface between non-magnetic or those which can generate this large spin-orbit torque and then interfaced with this 2D magnetic materials, I'm sure that at least some of the problems of the interfaces that occurs in metallic materials or insulating materials could be solved this way. So that could lead to efficient magnetization manipulation.
Thank you.
Okay, I don't know if we have questions on. Okay, so one more question. Yeah.
Thank you for the talk. In your conclusion, you have mentioned the possibility of thermally driven
yes.
spin current. Can you tell us some more about that?
Okay. So unfortunately, as you saw that I skipped some parts. So that was one way to generate spin current is basically to generate a temperature gradient in a magnetic material, which seems to, which basically generates an imbalance of the magnon population in the hotter and colder areas. And that magnon flow is actually a spin current. So that's a spin current that is without any accompanying charge current. And that could be harnessed. So it has been shown that the spin-Seebeck effect can pump spin into a metal like platinum and can be detected as an inverse spin Hall effect. But the possibilities of using the spin current to manipulate the magnetization is still yet not fully understood. So the spin current has been like a way to generate like a thermal power or just scientific curiosity, but not much research effort has been spent on employing the spin current to manipulate the magnetization in an efficient way as well.
So if there is no more questions, so thanks again to Chan for the very nice talk.